Ist das noch hingekriegt, dass das auch ein Typus gemacht wird? Von mir aus können wir starten. Piotr, are you ready?
Yes, I guess. We'll see.
So actually you are online already.
Yes, I noticed.
I give you a short introduction. I give everybody a short introduction about you, and then you start. Yeah.
Okay.
Welcome everybody here to the November edition of our Let Talk series. You know that we have every month one invited speaker during the semester. Today we have Piotr Didyk. He is an independent research group leader at the Max Planck Institute for Computer Science and Saarland University. So there's a collaboration between MPI and Saarland University where he leads a research group. And he did his PhD also in Saarbrücken at Saarland University together with MPI and was a postdoc at MIT for 2 years. And he's interested in perceptually-driven inputs for new output devices, which includes not only displays but possibly also 3D printing. I'm very happy to have him here and give a live talk from Saarbrücken. He's not here in person, but you will be able to ask him questions after the talk and chat with him. Okay? Piotr, it's yours now.
Okay. Thank you, Oliver, for the introduction. It's great pleasure to be here for you. Thank you for the invitation. I think organizing this kind of talks is really a great idea. So it's really my pleasure to be here with you guys and whoever is watching this. So yeah, today I will talk a bit about my research. This talk will be more like overview of my approach to what I want to do rather than specific projects and details. So, but yeah, anyway, so my research is essentially motivated by the recent development in many different kinds of output devices. So as we can see, currently we get much bigger variety of those output devices. They are different in many aspects. But what is interesting is that there is really many of them, and there are many differences in terms of capability. So if you look at them, we can of course reproduce much higher quality with current devices. They are much easier to use, but they also offers those new possibilities. For example, this recently emerging market of 3D printers shows that we quickly move from 2D printing to 3D printings, and this really gives people and even naive users a great opportunity to create stuff and to bring this digital world into real world. And even if we look at the specific kind of devices, we'll see that within each class of this device, there are many different subcategories, or those devices different in a different aspects. So for example, in the context of displays, we have displays with different sizes, but also with different capabilities. For example, we have those multi-view screens, stereoscopic screens. In terms of 3D printers, we have printers that are customized for needs, also for the budget that we have. So we can buy low price printers and print relatively simple things, but we can also buy those high-end, huge 3D printers that are able to do much more. Yeah, but I said those devices that are different with different capabilities. So this is, I think, also different from what we observed in the past, that now we not only get better devices, but also the customization of those devices is pushed to much larger extent. And on the other hand, if you look from computer graphics side, also not only computer graphics side, but in general, we learn how to capture real world. So starting from images, we can take high resolution to the images, but we also, for example, learn how to capture more complex data, for example, light field. Besides this, we also learn how to capture 3D information of surrounding us world, including also reflectance properties. And those two sources, we actually use in computer graphics, and those let us render, for example, super realistic images like those ones here, where we cannot really distinguish those renderings from regular images. And later, with this huge amount of content that we can capture, we also can post-process this content and create even more complex images and combinations where we can go to gigapixels photography. We can combine CG content with real content captured with cameras in the post-production tools for movie industry, or we can create very complex geometries. So on one hand, we have those huge capabilities in terms of how we can capture the data from real world. And on the other hand, we have number of those output devices that, as I said, they are different in many aspects. And what is really interesting for me is how to actually take this digital content that we capture, we post-process, and we obtain via different processes, and we use this to show this information on those different kinds of output devices, such as displays or maybe 3D printers. So in my research, this is maybe not really super accurate, but for me, I usually assume that we have an almost unlimited capabilities in terms of what we can capture. Of course, this is not true. If we talk to people that do rendering, of course, there are time constraints. We cannot render everything. But in theory, when we let those processes take long time, we can really currently capture really a lot of data. But on the other hand, on the output devices side, we have many different limitations. And what I mean by those limitations is, for example, the limitation in the display resolution. So if we think about it, take a closer look, if we look, for example, at 1 pixel those displays are composed of, and we look how this display patch projects on our retina, we'll quickly realize that the area that 1 pixel is covering on our retina is actually containing more than 1 photoreceptor. So there is approximately 9 to 12 photoreceptors that corresponds to high definition screen, which is placed 50 centimeters from our eyes. So this kind of gives us idea that although we can capture those high resolution images, when it comes to display, those displays are really limited and they cannot really address individual photoreceptors. Another example of the display limitation is, for example, the temporal resolution. So in real world, we are used to observing continuous motion, and we observe it in continuous ways, so we can track those objects and make this object steady with respect to our retina, with our fovea, so we see those objects sharp. However, in the context of display, those devices have rather limited temporal resolution, and this leads to many effects such as whole type blur or jagginess of the motion and so on. So again, we have currently high frame rate cameras, or we can render high frame rate content, but we cannot really display those things on current devices. In the context of 3D screens, there is this known limitation that we cannot reproduce a huge depth range that we might want to capture, but we usually have to squeeze the 3D scene or the stereoscopic content that we show on the screen to some smaller depth range in order to make the content comfortable. And last but not least, in context of the 3D printers, if we want to print some object, almost never, if we use current printers, we get what we want. And those differences there's a lot of differences in the appearance. So the resolution of current printers is not high, so we have lost geometry. We have slightly different appearance because the number of materials that we can use is currently limited. But there is also something more that we maybe cannot see, and this is beyond what computer perception in computer graphics considered so far. Those are mechanical properties. So because we have a limited number of materials, we cannot really reproduce all mechanical properties that we might want to convey. So in summary, no matter what kind of device or the output device we are using, and no matter how much better they will get, I believe that there will be always this gap between the content that we can create and content that we can reproduce. And there's a really extent list of limitations that those devices have, starting from spatial, temporal resolution, depth reproduction, as I said, for 3D and automultiscopic screen. And there is a lot of things that is there's now coming up due to the 3D printing technology and how actually reproduce the complex three-dimensional objects so they actually look and feel plausible. So really the question is how to do this translation process. But there is this one more thing that I talked already and mentioned a bit. There's no matter what kind of objects we are going to reproduce, most of them, not all of them, but most of them will include some that will involve some human interaction. So what I try to address also in my research is to take this into account. So I try to remember that whenever we do this translation process from digital content to output devices, there's at the end a human observer and a human sensory system that is involved in the perception of those objects, of this content that we are creating. And as I mentioned, there are those limitations on the output devices side, but there are also many limitations on the side of human sensory system. And just again, to give you just brief idea what those are, is, for example, here there is a limitation of the human visual system to the color perception. So if you look at this image and I ask you what kind of colors are used for reproducing those two words, you will likely say that the one on the top is blue and the other is on the bottom is green. But in fact, if you look closely, those two colors that are used for actually creating those two words, they're exactly the same. So this kind of shows that we are often fooled by our perception, and very often what we actually see is not what we actually get in real world. The another very frequently used properties of the human visual system is so-called contrast sensitivity function, which essentially characterize which kind of patterns we see or which kind of patterns we don't see. And this is related to the contrast, to the magnitude of the contrast, and frequencies of the contrast. And many of the techniques for preparing content for displays actually rely on those findings about the contrast sensitivity function. And on top of it, there are also many illusions. So for example, this is a standard illusion that's often shown. There are those two blocks atop of each other. And if I ask you what color are these or what gray value are these, you will likely say the lower one is much brighter than the one in the top. In fact, however, when you cover the transition between those colors, you will quickly realize that those two colors are the same. So again, the main message here is that human visual system, and not only human visual system, but in general sensory system, has many limitations, and what we see, what we perceive often is different from what actually is reproduced. There's also one more thing that I want to mention. There's a human preference. So in many aspects, the human preference plays a big role. And just recently, there was a huge debate. I mean, there is still a huge debate about the frame rate, because there were new movies released in high frame rate. And you can create a movie in 24 frames per second. And you can, I'm not sure whether you see it, this is 48 frames per second. Probably you don't see it, but anyway, there is the debate. Of course, 48 frames per second is closer to reality, but at the end, what people want to see, it's not really clear. Some people want 24, some people want 48. So really, it's first thing is about the limitations of the human visual system, but then at the end, you need to also take into consideration what actually people want to see. So yeah, so there are those limitations on the human sensory system. And what is interesting here is the limitations on the human sensory system and the limitations on the output devices side, they are usually not the same. And there's the place where we can play a game and try to trade those limitations. So we can use certain limitations on the human sensory system and use them in a favor to improve the perceived quality on the output devices. And this is essentially what I would like to show you now. And the standard way of doing this and the approach that we are trying to do is to learn something about the human sensory system. Simply speaking, we may say that we want to some extent simulate the human sensory system, build models of them to understand how it works. And then we want to include those models into what we call perceptual optimization, which essentially is translating this digital content into output devices and try to optimize for the best quality, but not for the best quality as can be measured on output devices, for example, on screen, but as measured as a perceived quality observed by the human observer. And the standard the way such a perceptual model works and what can be a simple task that such a model should be able to do is essentially, if we have, for example, in context of displays, if we have a reference image that we want to show on the screen, and we have certain display limitations that cannot really, which do not allow us to show this image on the screen, and we have two instances, so to say, of this image that can be actually presented on the screen. We want to essentially be able to judge which one will be closer to the reference. And of course, we can use a standard numerical differences, but it turns out that those numerical differences very often do not meet the values that are actually reported from the people. So here, maybe if in the variant B, we just reduce brightness slightly, increase the brightness slightly, in the terms of numerical difference, it can have a very similar impact as, for example, reducing the resolution. But in fact, people are not that sensitive to the luminance changes. Therefore, this numerical difference here doesn't really simulate the perceived difference really well. So in this case, we would just like to tell which variant A and B is better. And this is one of the tasks that such perceptual modeling should be able to do. And if we think about it, such models are really in the heart of many things that we are using currently. So for example, MP3 codec, what really has insights, it's some model that essentially tells which of the signal will be heard by a person and which will be not heard. And then based on this, we can remove the information that will be not relevant for human system, for human sensory system, and therefore we can compress this information and make use of such things. And yeah, just to mention this again, the same things happen in JPEG. In the deep down in the JPEG compression, we have a model that can tell which things we will see and which will be not perceived. So it's really about telling the differences between two images and saying yes, what will be visible or not. And then if we have such a model and we want to do this perceptual optimization, we can do it very naively. So we have a reference image that we want to display, and then we have a number of different variants of images that we are able actually to display on those screens. And if we have this model that can predict those differences, we can simply compute those differences and run some optimization method, which can choose the image that best reproduces the reference image in the perceptual sense. So really what we are talking here is this translation process, which is governed by this perceptual optimization and by the knowledge of the human visual system. So now I would like to give you a quick overview of 3 examples where we use actually such approach, and it was successful in doing so. So first I will talk about the spatial and temporal resolution. And in this context, we had a project where we wanted to address the problem of limited resolution of display devices. So as I said before, we can capture high resolution content, but we cannot really display it well on the screen. So usually what we do, we take high resolution image, then we have to filter out the information, meaning here high frequency information that we cannot reproduce on the screen. So we get kind of blurry version of this image, and then we downsample this image, and then now we are able to show this image on the screen. But as I was already mentioning before, this is a pity, because if we look at the screen, there are really many receptors that are looking at the same pixels in standard setup. So there could be really a hope that if we have high resolution displays, there would be a way to convey more information and to address individually larger number of photoreceptors. So what we wanted to do in this project is essentially to take high resolution image and then do something to it that when we show it on the screen, it actually creates this impression of high resolution image. So we cannot really show the high resolution image on the screen because it's low resolution device, but what we aim for is really this impression of high resolution image, which is created at the end in our human visual system. And in this context, what we did, we came up with this idea of decomposing the image into multiple lower resolution images that are shown over time. And we wanted to use here the temporal averaging that is done by the human visual system. So if we go back to the scheme of the translation process, essentially the input to our method is high resolution image. And then we want to, as an output, we want to have a number of low resolution sub images that we show on the screen. And what we want to account for is temporal integration done by the human visual system. So this method, I would just here mention that this method works only when we deal with moving pictures. So if we consider only static images, this doesn't work. I will not go into details here, but yeah, it works only for moving images because only then you can play such tricks as we do. So just to explain you how it works, is let us consider those 2 pixels and 3 photoreceptors that are looking at those pixels. So now, if we change the content, if we change the content that is displayed on the screen, but at the same time the content is moving on the screen, so we have some motion, our human visual system is well trained to track the object that is moving on the screen. So if we show a moving object, essentially what will happen is the values of the pixels will change, but also the positions of those receptors will change with respect to the initial position. So as we can see here, if the object is moving, I can change the signal that is shown on those pixels, and at the same time I can move my photoreceptors move. And now the interesting observation is that if those receptors were not moving, so if they were static, no matter what kind of signal I would show on the screen, at the end, those 3 receptors that were falling in the same pixel, they would receive the same signal. But here, because they are moving and they cross the boundary of those pixels, actually we can address almost each receptor individually. So we can see that because those receptors see slightly different color over time, at the end of the cycle, what those colors averages to is slightly different. So this kind of shows that each of these photoreceptor can see something slightly different. And this was the motivation to our project, and we formulated the problem as an optimization problem. And first we created a model that essentially takes those sub-images and the motion that we perform and builds an integration model that can predict the image that's actually perceived on the retina. So it takes into account the motion, it takes into account the sub-images, and it predicts what we see after this temporal averaging of the human visual system is done. And now if we have such a model, it turns out that this model can be easily written as a system of linear equation. So now if we want to compute those sub-images that give us the impression of looking high resolution, what we need to do, we have to turn this linear system of equation into optimization. So we give as a matrix that prescribes describes this integration model. We essentially create this matrix using the information about the motion that we have in the scene. To the right-hand side, we just give this high-resolution image that we want to perceive, and we simply optimize for those sub-images that we have to show that after the integration, they give us high-resolution image. And once we solve this, we can, for example, obtain such a result. So those are 3 frames that we optimized. And you can see that each of this frame on its own doesn't convey any information. It's actually full of aliasing, but this is a good sign because this aliasing actually is a source of high frequency information when this after this temporal averaging happens. But what we simulate after showing those 3 frames on the screen in the rapid succession, what we actually can see is that those images average on our retina to something that actually we can read. So although those 3 images don't convey any information because the resolution of those pictures is too low, after this temporal averaging, we actually can obtain high resolution. We perceive actually high resolution image which we can perceive well, and we can actually read the text. And so this project was done some years ago, and that there was some new developments on the technology side. And one can question, why do we need high resolution if we already such techniques if we have already 8K display and we don't even have content for this? Well, the thing is that as soon as we will start moving from standard screen to something which is more light field screen, so for example nowadays we have those maybe not very common, but there are those automultiscopic screens which can show actually multiple views, then we are still lacking number 4 pixels to actually build those screens. So I believe, although maybe for the standard application, maybe one is right if it says that further improving the resolution is maybe not that important because we have high resolution devices already, and maybe 8K weighs too much comparing to what we need. But if you think of those light field display, multi-view displays, those people that work on those displays, they still struggle with the fact that everything is low resolution. Even if you take head-mounted displays like Oculus Rift, if you put this high resolution screen in front of eyes, you quickly realize that the resolution that you need is not 2 times, it's not 3 times higher, but it's maybe 10 times higher that you actually need. So such techniques, I believe, will still find use in such context. Okay, so this brings us to the topic of stereoscopic and auto-stereoscopic displays, which I will talk about now. So in the context of stereo, we show the stereoscopic images by showing 2 different images that are taken from 2 different viewing positions, and we show them to left and right eye. And the stereoscopic impression is created essentially thanks to those disparities, so thanks to those small differences that we have in both eyes. Now, the thing is that this is not the only source of the 3D effect that we get. That's not the only cue that contributes to depth perception. So those small disparities is essentially called binocular disparity, and accounts for how different objects and different depths project on our retina and where they end up with respect to each other. But there is a number of other cues that also give us a good perception of depth, and those are those ocular depth cues. Maybe some of you have heard about accommodation, which is essentially the shape of the lens which set the picture that we see in focus. The other is vergence, which is essentially the angle between our optical axis, and those 2, they are also very strong depth cues. And there are also those pictorial depth cues that we have in 2D images, like occlusion, size, or shadows. Now the thing is that in order to provide good stereoscopic content, those cues have to be in agreement. However, on 2D screens, we can only reproduce those binocular disparities and pictorial depth cues. The ocular depth cues, accommodation, invergence, they really require 3D space. We cannot really reproduce them on the standard 2D screen. And to just give you a more insight why is it so, let me just show you the simple example when we have eyes looking at the screen, and there is one object that we show in different position of the screen for both eyes to create an impression, in this case, of image floating in front of the screen. Now, the problem is that if we look, so this is what binocular disparity would tell us, that this object is floating in front of the screen. If we look at the divergence cue, it will stay with agreement because the angle between the optical axis will be correct. But if you look the accommodation, so where we actually accommodate, where our eyes set focus, this is actually the plane of this is the depth of the screen. And this discrepancy between those cues, mainly accommodation and divergence, this creates a viewing discomfort because they remain in disagreement in the stereoscopic setup, and they're actually coupled in nature. This discrepancy between them creates a viewing discomfort, which fortunately can be tolerated in some region around the screen, but this range is very limited. So in fact, what you have to do if you prepare the stereoscopic content, you have some objects that are further from the screen that this comfort zone allows, you actually have to bring those objects into that comfort zone to make sure that people will not experience viewing discomfort. So here, if you think again about the translation process, what you have as an input is some representation of the stereoscopic content. It can be depth map together with images of disparity. And as an output, you have to reduce the depth map, that you reduce the range of depth that you show on the screen, because you usually cannot reproduce the depth range that you capture in the real world. And to do this, we essentially want to account for sensitivity to disparity of the human visual system and to limits of the comfort. So how much people can tolerate of this depth range. And so we address this in one of our work on modeling disparity. And the one thing that this and other models for human perception rely on is the fact that deep in the brain, what we are doing very simple image processing. And it turns out that similar to luminance perception, also disparity perception, what human brain does is essentially it has a different receptive fields that are tuned for patterns with different frequencies. And this essentially gives us hint that what human brain does is actually some kind of decomposition of complex images into different frequency bands. And then the brain kind of processes each of these bands separately. So now if we want to simulate how such a processing works, it turns out to be sufficient to do experiments on simple patterns, because here the brain decomposes this image into different frequencies. What we can do, we can measure the performance of the human visual system, for example, on sinusoidal patterns. So this is easy to do because the space of different sinusoids or sinusoidal depth corrugations in this case is not that large, because this is controlled by essentially the amplitude of disparity and the frequencies of the disparity corrugation. And then we can explore such a space, and we can essentially measure how the human visual system responds to different signals. And in this case, we can measure thresholds. So what's the smallest amplitude that is visible by the observer, or what's the delta of the amplitude that people would perceive, would see. And based on such measurements of sinusoids, we can apply them directly in this frequency decomposition. So in fact, what we did some experiments. I will not go into details, but we did some experiments on the sinusoidal patterns. And then, because we know that human visual system performs this kind of processing, we can follow it and at the end, what we do, we take the depth information. We similarly as the human visual system, we decompose it into different frequency bands where we can actually apply this knowledge that we gain in the experiments done for sinusoidal depth corrugations. And then we can compute so-called perceptual space of the depth, where the depth is essentially at each band, at each frequency band, is measured in some perceptual units. We call them just noticeable differences, where one JND would mean something that is barely visible. And then if we have such model, we can essentially do many different things. For example, we can compare stereoscopic images because we can perform such a decomposition for two images and we can compare them. We can compare those JNDs and know what's visible. We can also remove the signal that's invisible, because everything, we know that everything that would be below this one just noticeable difference is invisible. So for example, we can remove it for a compression purpose. One interesting thing that we did with this model is something which we called backward compatible stereo, or just enough stereo. And essentially the observation was that not everybody likes the stereo. And if you have two people, one of them likes stereoscopic images and the other doesn't, it usually you have two choices. Either in both cases, either the person that doesn't like the stereoscopic image will see those color artifacts while the other person will enjoy the stereoscopic impression, or the person that likes stereoscopic impression will not see stereo because the other person wants to see a clear image. What we propose is something which is just enough stereo. I'm not sure how much you will see on the video that you see there, but essentially we're able, according to our prediction done by our model, we can limit the disparities that we use in this image to minimum, just to make sure that the stereoscopic effect is visible. And this allows us to apply as little stereo as is necessary to see. So that's good for the person that likes stereo. But on the other hand, the person that doesn't like the stereo and, for example, doesn't wear the glasses, necessary glasses, that person doesn't see that much artifact. So if you compare this and this is again, this is very tiny artifacts here, but if you wear glasses, you actually have a quite good impression of stereo. We also did some work concerning the temporal domain, as those are only static images, where the input is the image sequence and the output is optimized image sequence that you show over time. Here, the problem that we consider was stereoscopic cuts that can be very disturbing because you're exposed to very rapid changes of depth. So something that you cannot really observe in reality, because when we look around, we can control what we see and we kind of predict on what kind of depth we are verging at every moment in time. When we watch the movie, we don't have, we don't know actually what's the intention of the director, so we can be exposed in very rapid depth changes, which can be very annoying. And just to give you some statistics, such a transition time between one depth to another can take up to 500 milliseconds. And it turns out that the average scene cut in the action movie is around 3 seconds. So this just gives you an idea how much time you lose on just changing the depth at which you're focusing. And in this project, we were investigating and optimizing those sequences depending of the performance of people on focusing on different depth levels in the context of stereoscopic content. So here we accounted for the human interaction and performance. And what we essentially did, we ran again a bunch of experiments where we exposed people to stimuli shown at different depths. So that was more or less the experiment that we ran. And then from that, we could derive the model that essentially predicts how long it takes for people to change the divergence from one depth level to the other level. And based on this, we can evaluate the content, so we can, for example, tell how much time people will lose for this reverging, or we can also advise the techniques for actually optimizing stereoscopic content to minimize the time and efforts that people need to put into watching this content. So far I talk only about the visual stimulation, so I talk about the displays. Now I want to briefly talk about the 3D printing, which doesn't only provide us with visual simulation, but also we can touch those objects and we can examine those objects as those are real 3D objects. So I will now talk a bit about the multi-material printing and the work that we've done here. So currently with such printer as this Object 500, we can print a big variety of different objects. The problem is that whenever you want to print such objects, it's almost, you really require an artist who will do this design for you. This is not really, those objects that are here, they're not really produced by naive users. And the problem with this is that if you look at the multi-material printing and you want to print your objects, the first thing that you realize is the printer doesn't see your object. It doesn't know what you want to really achieve, but it only sees a bunch of pixels that it will be filled by different materials. So essentially what you have to solve is you have to solve for the assignment of multiple materials that you have on your printer to those voxels that will be at the end printed. And in this context, the translation process, we consider this functional specification. So the user has to specify the geometry and some high-level properties like reflectance, mechanical properties, and you want to translate this data into something which is understandable by the printer. So this is usually done in this, as it's shown here, in kind of optimization loop. When you have the goal that you specify, then you have a parameterization of your geometry over which you optimize for different materials. Then you usually have to be able to simulate this assignment, how this object would look in real world and how people would interact with this object. And then you have to, on top of it, you have to have optimization that essentially optimizes for this material assignment. So the brute force approach is to have this per voxel material assignment. But you quickly realize that if you try to optimize the material assignment on per voxel basis, this will explode. This will have there's really humongous amount of possibilities that you can consider. So the work that we did 2 years ago was about parameterization of those 3D objects for such kind of specification. So instead of having per voxel parameterization, we created so-called transducer tree, which in fact is nothing else than hierarchical space subdivision, but it's really tailored to the applications in 3D printing. So in this case, the object can be broken down into several pieces by those internal nodes. And those internal nodes, they consist of, in this case, 5 different techniques for splitting the volume. And then the leaf nodes, they encode the material assignment. So this is the example how you can break this bunny into such representation. And now the thing is that instead of optimizing for the individual voxels, you only optimize for those material in those bigger chunks of the volume that are at the end of this tree. And you also optimize for those parameters of those subdivision components. So for example, if you have the stratum, which divides the object into outer shell and the inner part, you may optimize for the thickness that this shell has. And with this such a reparameterization, we were able to, in a pretty easy way, come up with different fabrication techniques. So here, for example, are results for texturing. But we can also combine those things and do, for example, texturing and subsurface scattering. So this is again texturing. I will just browse it maybe. This is for subsurface scattering. And the nice thing here about this parameterization and this framework for creating those fabrication techniques is that you can easily combine them. So this is, for example, here is the producing smooth caustics. So this is the work that, this is essentially, we show that we can, with such a simple approach and simple specification, we can reproduce the techniques that were already presented before. But what is more interesting, we can actually combine those things. So for example, texture and mechanical properties, we can combine them into one tree. We can take those trees and we can create a completely new fabrication techniques. So here is again texture and caustics. We can combine two and jointly optimize for the material assignment. Okay, there's just one more thing that I would like to mention that I'm currently working on, and that's the field that I would like to expand to a bit. I think it's worth noting that in the slope we have this comparison, and currently what is done in this box, those are very simple metrics like image distance, mesh distance, curve distances. But in fact, if you think what I said before, many of those objects are going to be handled by the humans, and humans will interact with them. There is really question whether we should not investigate those metrics and actually try to come up with some smarter metrics that will model the human perception in a better way. And possible benefits of designing those better metrics for fabrication is that we probably may get a better translations algorithm, so the perceived quality will improve. And in fact, we also may get a more intuitive modeling tools, because if you think, for example, of tools that assign different materials with different mechanical properties, those tools are not really intuitive for naive users. Maybe they want to know which material is softer, which is stiffer, but they don't want to tune hundreds of parameters that those materials have. So I think there is also interesting work to be done there. Okay, so to conclude, I hope I convince you that producing the right content is an important problem. And if you take into account actually the human observer that at the end interacts with this content, you can increase the quality, you can improve the user experience. And in this context, the perceptual models are very relevant when you consider this human interaction. And just to give you this overview on this perceptual modeling that we try and to do, and what are important components, is first of all, if you want to do such stuff, it's important to pick up the right representation. So we usually don't deal with complex images. We kind of try to represent those complex images or complex geometries with some simple basis functions, so to say, someone can call it. So for example, it can be Gabor patches. And then we have to run user experiments where we measure some phenomena, some thresholds, how people see differences and so on. And we really want those models to be computable forward and backwards. So we usually want to predict what people want to see, predict based on the content that we show what people will see. But we also want to, based on what we see, we want to predict what the content we would like to show on the screen. And yeah, in the context of perceptual optimization, we usually try to design the online processes. So most of the techniques that I was showing, they run in real time. This is important for example, for graphics application. And we also care that those methods adapt to different content, different devices. And also we account for observer personalization. So for example, with this just enough stereo, this was kind of example of observer personalization. Okay, so just I would like to mention people that work with me, and without them, I think I would be not presenting this work to you today. So yeah, there were many people involved, and yeah, with this, I would like to thank you all for listening to.
Okay, thank you. Any questions? Mark.
So I'm wondering what the role of the user is in your research. So for instance, how good are the models that you already have for temporal perception? And do you actually need the user for every experiment that you do, or do you already have good models for describing, for instance, the temporal perception?
I mean, this really depends what you want to do. For example, for this, I don't think we have good models. So anytime we come up with some idea for the project, we usually have to run new experiments and build some new models. And the problem is that all the models that we come up with, they are very specific and then are very targeted to certain phenomena. So I'm happy that this is, you know, so there are also those people like hardcore perception, people vision perception, they would run even more specific experiments just to show certain phenomena. We take them a bit step further to actually make them applicable for complex images. But I don't think we have a complete model that would, for example, model completely the temporal aspect of the perception. Yeah. So, for example, in the project that I shown here, this was really something that was saying that was letting us know or was predicting what kind of signal, how much we can vary the signal over time, so we see the steady content instead of changing content over signal over time. Yes. So this was very specific, and I think, yeah. So as I said, like, in any of this project, the user, I think that's what we was asking about, plays an important role in the sense that we almost always have to design new models. Yes, so we try to kind of bridge those things and try to build models that are more general. But the more general you want to build those models, the more difficult it gets. So we are rather considering like smaller aspects and then taking advantage of them. Yes, it's also always the question how accurate you have to be in modeling those things, because it's known that every model is incorrect. Yes, you cannot probably be perfect, but also what we try to do, we try to show that, you know, even we make some assumptions and simplifications, at the end we always not only rely on those models that we build, but we validate them in the context of the application. Yes.
Okay, thank you.
Any more questions? I have a couple of specific questions, and I think people warm up later on. You mentioned that you always or often use artificial stimuli like Gabo patches to do your experiments and not complex images. For example, in your work on model of eye vergence response, you use artificial stimuli to simulate disparity. Do you think that the image content is important for?
Yes, it is. So that's what we observe. Like doing it for simple stimuli, as I said also before, it's easy. Yes, because you have really the parameters that you can vary. Yes, for example, for this Vergence project, it was simple patch with some kind of noise, and we simply varied the two depth levels between which the transition happened. But I mean, there is much more to it if you go to complex images. Yes, so if you consider the video, people of course build some mental image of the entire scene. And you know, it's not. They do also saccades, so something that we didn't consider because we have only patches that were aligned, so they were appearing at the same location on the screen. So they were not doing really saccades. That would be another parameter that we could use in our stimuli. But then, of course, when you so those simple experiments that we run, they're really nice, and you know, we can control it and build model. And of course, I think where you're going is that, you know, if you try to apply them to complex images, you find out that they are not accurate. Yes, they are not. I mean, they will not predict exactly what you can predict for complex stimuli. But this is something that you have to kind of, I think, live with. Yes, if you do this kind of things, I mean, you can go ahead and do it for complex images, but those experiments become really hard. You can imagine that, you know, instead of having those patches, you play a video and you let people watch, and you kind of want to even like use maybe some machine learning approach to build such models. But we tried something like that also in the past. It's difficult, yes, but it's also true that if you do the modeling for a simple stimuli, you will have not the same performance of this model on the complex images. That's why I said that what is important in all those projects is that at the end, you validate those models in the context of application. Yes. So for example, also this project on predicting on the disparity perception, we noticed that when we model this thing and then we were evaluating in the context of complex stereoscopic images, we noticed that as the number of depth cues increases, so as you have more and more information like shading, occlusions, and things like that, the prediction of the model also deviates from the human responses, yes. But still, if you can show that your things correlate well and they're not too much off, I think this is, this is what we are essentially aiming for, yes.
Mm-hmm. I also didn't get the idea of just enough stereo. So basically, you're reducing the disparity to support people that are not so interested in stereo but in mono. But on the other side, with just enough amount of disparity to do depth perception, to have the depth perception, you cover only very little depth range.
Yeah. So the idea was to we know more or less what kind of signal people are most sensitive to in terms of depth. So we essentially were adding this information instead of some, for example, low frequency information that people are not that sensitive. Of course, this doesn't convey the entire, that it doesn't give you the same impression. We did some experiment where we ask people to compare our technique with the real stereo, yes, and we can show that you can largely reduce the overall disparity range by preserving very similar depth impression. Of course, it's not the same. I mean, there is no magic, yes. If you remove some information, it's missing, yes. The only question is which information you remove, yes. So the goal is to remove this information that's least crucial for you.
Mm-hmm.
But of course, yeah, if you look at these images, if some of you is interested, we have those images and those examples on the website. You can use any stereo devices that you have, and you can look at those images, and you will see that this is not the same, yes. But if you have to compromise two observers, you have choice in terms of what you're going to show and what you're not going to show. So you can always do like those better or worse decisions. So this is what we try to do there.
Other questions? One last question from my side: the spatial versus temporal resolution project.
Yes.
When you consider a particular frame rate, like 24 frames per second, and one frame appears on the screen for a certain amount of time, and you are looking at moving pictures, so basically your eyes follow the motion, and while you have a fixed image during your frame time on the screen, your eyes keep on moving.
Yes.
And that causes motion blur.
Yes.
Did you consider that in that work as well? Because